Assalamualaikum and good morning, guys. So here we go to the last section of the course, or I would say the last topic of the chapter, surface integral. So we go to the last theorem where we have a Stokes theorem. So last time, in line integral we have Green's theorem. And then for surface integral, we already have looked at the Gauss theorem. If your surface is a closed surface and you have the solid, so in order for you to apply or to compute the surface integral, so it is more easier for you to apply the Gauss theorem or divergence theorem, because the formula is related to the divergence. Okay, so now we go to the last theorem. We have a Stokes theorem. So the Stokes theorem is actually the extension of the Green's theorem, where we know that for Green's theorem, we can apply that theorem for 2D system. Your vector field is in 2D, or when you have a curve on 2D. Okay, but then for 3D, you cannot use Green's theorem. So now you can use something. The behavior is similar to the Green's theorem, but it is in 3D. So we have a Stokes theorem. Okay, so what is inside the Stokes theorem? So as you can see here, this is the Stokes theorem looks like. So the way you can implement the Stokes theorem is not just like Green's theorem and also Gauss theorem. As we know that for Green's theorem, that is applicable for line integral. If your curve is closed curve, then it's easier for you to apply Green's theorem. Okay, where you have to apply the double integral, isn't it? Qx minus py. Oh, sorry. Yeah. Qx minus py. Okay. And for Gauss theorem, it is about you have surfaces. Okay, many surfaces, and the combination of the surfaces, you have the solid. As we know that, how can you say that it's a solid if you have a closed and bounded surface where it's coming from more than one surfaces? So to compute the surface integral more easier, so we implement the Gauss theorem, which means that you have to apply the right side of the formula, which is the triple integral, isn't it, of the grad dot f. Do you remember that? Okay, now for Stokes theorem, it's not something that easier for you to easier way to be done. It looks like they will say but depends on the situation. So normally if the instruction say that using Stokes theorem evaluate the line integral, so meaning that for you to calculate or to show me the answer on the paper, you have to work on the formula on the right to obtain the left one. If the instruction say that using Stokes theorem, compute the line integral, this one. So meaning that on your answer script, you have to obtain or you have to show me that you compute this one. But sometimes they can ask you, using Stokes theorem, evaluate this particular thing, which is the surface integral of the curl f dot n ds. Meaning that for that, you have to show me your calculation is about line integral, where your C is a closed curve. Okay, how can we know that it is a closed curve? Because the symbol here on the integral, so it shows us or it tells you that your curve is closed if you have a small circle here. Okay, so okay, before we look at an example for the Stokes theorem, so we want to understand what is the symbol all the symbols on the Stokes theorem. So here C, you can see the C here, right? So C be any closed curve in 3D. So in this case, if you look at the statement here, so the Stokes theorem deal with the problem of a 3D curve in space. Okay, so you have a 3D curve in space and the line integral around such a curve. Okay, so if you look at here, it is a relationship between the line integral and surface integral for the same vector field. Okay, so now what is inside the Stokes theorem? C be any closed curve in 3D. So C here must be closed curve in 3D or in three-dimensional system. And you can see the sigma here. We know that sigma stands for surface. So, and let sigma be an oriented surface. Okay, oriented surface. What is the meaning of the oriented? So, you can obtain the normal to the surface. Okay, oriented surface bounded by the C. For example, your surface is a plane. Okay, I give you a plane. So this is your surface sigma. So that surface sigma, so this is your surface. Okay, close surface in 3D. Surface in 3D. Okay, let's say this one z equal to 3, for example. So the surface sigma is bounded by the boundary. So what is the boundary of this surface? So the boundary of this surface is a closed curve. So you can see this one. So this is one curve, a second curve, third curves, and the fourth curve. So the combination of all the curves, you have a closed curve. So that is given by C. Okay. So how can we relate the surface sigma and the closed curve C? Alright. And then the surface sigma be an oriented surface bounded by the curve C with unit normal vector n. So you can obtain, so on the surface you can always obtain the normal vector or unit normal vector to the surface. Okay, so imagine that there is what we call that, okay, a vector field. So let's say this is your vector field given by the vector f. Okay, f is a vector field that continuously differentiable. Okay, so then we can see that the value on the left, which is the value of the line integral given by the closed curve C, is equal to the surface integral of the curl f, okay, over the surface sigma. So we can see that sigma can be any surface bounded by the curve C. So as I mentioned before, Stokes theorem reduced to Green's, which means that if your curve, okay, this one the curve is on 3D, right? If your curve on 2D, so it reduced to Green's theorem. Okay, actually, if you realize for Green's theorem, you have the qx minus py, right? So actually qx minus py is coming from the curl f, but because of it is 2D, so the key component is 0. So that means that you can only compute the qx minus py, which is part of the calculation of grad f, where the rest is 0. So that's why you can't see the curl f in Green's. Actually, the formula in Green's theorem is actually coming from this formula. Okay, because that k 0, so the component I and j, they are 0. Okay, so what is the integral given? You can see this is integral, the left is line integral, the right is the surface integral. So this integral give you the circulation. You know that curl f means circulation, so the circulation of the vector field f. Okay, imagine you on the surface there is a vector field f, so the circulation of the vector field f around the C, so that is the thing that you compute from this formula, from the Gauss from the Stokes theorem. We are computing the circulation of the vector field F around the curve C. So that is the physical meaning of the Stokes theorem. So this is the Green's theorem versus Stokes theorem. So for Green's theorem, so this is for Green's theorem that we have already applied before this. So the formula is actually, this one is curl F, but we just use to simplify our work. Okay, I just check down here. So for Green's theorem that you already applied before this, so you have a closed C on 2D, right? On 2D. So it is given by double integral and qx minus p y dA over the region. So qx minus py is actually curl F dot k. Okay, but since this one a bit messy, so we just simplify our to reduce the complexity. So we just compute the qx minus py. So for information, qx minus py is coming from the curl F dot k. Okay. So if you look at our previous discussion on the Green's theorem, so we are actually computing the circulation. Okay. So in this case, from the Stokes theorem, they said that the total circulation around or along the curve C is the same as the total circulation inside the surface sigma. Okay, so that is the physical meaning of the Stokes theorem or Gauss theorem. Green's theorem. But the difference is Green's only on 2D and Stokes is on 3D. Okay. So they said that each point, so you imagine inside there is a point here, point and point. So so it can be in this direction. So if you look at here, so they are twisting in this direction, and the other one is in this direction. So the total of the twisting or circulation of each of the point can be cancelled out, and then it just when they are always cancelling each other, so the left is only the total of the circulation which only lying on the boundary here. Okay, so that is given by the line integral. Okay, so in a more simpler way, if someone asking you what is the physical meaning of the Stokes theorem, so the Stokes theorem says that the total circulation along the curve C, imagine you have the circulation of the vector field F, so the total circulation along the C is the same as the total circulation inside the total circulation inside the surface sigma. So that is the physical meaning of Stokes theorem. Okay, so for example, you have instead of we have a plane, we can also have the let's say I give you hemisphere. What is the hemisphere looks like? So we have a hemisphere for any radius, so that is hemisphere. Let's say radius 1. Okay, so as we know that when we say that we have hemisphere, so this should be shaded, right? That is part of the surface. Okay, but it is open because they didn't say that we have a solid. So we have just a open surface, which is a hemisphere. So what is the curve? Can you determine what is the curve which becomes the boundary of the hemisphere? What is the boundary where because for when you want to apply the Stokes theorem, you must be able to determine the C, the closed curve, and the surface sigma. So in this case, your surface is given by the hemisphere. This one. And where is your closed curve C? Where is it? This one, right? So this is your C. Okay, so that is your C. Okay, so as mentioned here, consider a hemisphere bounded by its lower circle. So bounded by this circle, lower circle, and we have a cone. At the same time, we have a cone. Okay, where the size is the same on the. So let's say I have this different color. Okay, I have a cone. So let's say that is one. The cone concave down, or maybe I have a cone concave up like that. So if that is the case, they will be between the hemisphere and the cone concave down or the cone concave up, they are sharing the same. Close curve, right? Which is the circle. Okay, so that what is the meaning of this statement, which is bounded by the same circle. Okay, so according to Stokes, both regions would have the same circulation because they have the same boundary. Okay, so meaning that in this case, the hemisphere and also the cone, they have the same circulation because they have the same boundary. So that is the statement, but actually you can compute. Okay, so normally just I'm talking about for the sake of exam, so you just need to compute. So we will give you a vector field F, and we will give you some information regarding the sigma and also the curve, and you have to just compute the Stokes theorem. So which one you need to compute? So it depends. If they ask about the line integral, then you have to compute the surface integral. Understand? If they ask about the left one, then you have to show us the right one. If they ask about the right one, then you have to show us the left one. So I will show you some example later on. Okay, now look at the example 519.